Here at Study Lab. Welcome back to our series on how to make an operating system. Last time we discussed some basic assembly instructions, and I was supposed to continue that talk, but I decided it's better if we get into the bootloader a little bit. And as we code our way through the bootloader, we're naturally going to be discussing some other assembly instructions. I'm not going to get into the actual code here. In this part, I'm just going to discuss the basic structure of a bootloader, show you how I can test this bootloader, and a few other important aspects before we actually start coding and explaining what's happening in here. So the bootloader contains exactly 512 bytes and is saved on sector 0 of a drive. So it can be on a floppy disk, on a CD, or on your hard drive or SSD. When the BIOS detects a bootloader on one of your drives, it loads it into memory at this address here. So at basically 7C00 in hex, and what you see here is segmented memory addressing. So this first part here before the colon is called memory segment, and this last part here is an effective address or offset. So basically the way this works is the CPU multiplies the segment by 16 and then adds this offset, and the resulting sum is used as a memory address. This was used in 16-bit mode for being able to access a larger span of memory, basically, because using just a simple one-word memory address can only get you so far, right? You can only access from 0x0000 up to 0xFFFF, and that's not much of an amount of memory that you get access to. So the funny thing is, depending on your BIOS, sometimes it loads your bootloader here at segment 0 and offset 7C00, or it loads it at segment 7C0 and offset 0. But these two are actually equivalent, because if you multiply 07C0 in hex by 16, the result is 0x, the result is 7C00, okay? And if you add a 0 to that, it's 0x7C00, which is the same as this offset here. So those two things are equivalent. Now this here is just an NASM, a net wide assembler directive that tells the assembler that we're going to be working in 16-bit mode, so that all the default operand sizes here will be 16-bit or one word. Then there's this section Dot Txt Directive, which we actually discussed in a previous video. It's just a way to tell the assembler that what follows is actual code. Finally, you can see that I actually integrated the variables directly into the code segment. So I'm not using a separate data segment right now, because for some reason that will mess up some of my calculations in here that I will explain shortly. So I just have all the code and all the variables in the same section. And you can do that as long as you make sure that the data never gets executed as code. And the way I'm preventing that here is by jumping continuously at the same memory location here. So basically I'm doing an infinite loop here. The dollar symbol, as I've explained previously, is basically just a placeholder for the current instruction's address. So this jump instruction jumps back to itself over and over again, so it basically just hangs. And this way the execution stops here, and it never gets to this part here where we have our variables. I'm going to explain this very briefly, but before I do that, let's see what we have in our data segment here. This part here is not important for now. It's just a string, hello world, and the string length. But then these two things are important in the context of our bootloader. So I have two labels here. These are optional, so you can just define data here like this. You don't need to apply a label to those variables or data streams unless you want to reference them in your code, obviously. But anyway, I have a label here called 0 fill, and I labeled it that because that's what it does. So remember that our bootloader must be exactly 510 bytes in 512 bytes in length, sorry. So to ensure that the bootloader is exactly 512 bytes, we need to fill the rest of the bootloader with 0, or with whatever you want basically, but 0 is just the conventional way to do it. So we need to fill it with 0 until we get to our 512 bytes. We're not sure how much our code will be occupying. So unless you want to count all your bytes here and make sure you code exactly 512 bytes, it's just easier to apply this trick here and automatically fill all the remaining bytes up to 512. So I'll explain this instruction in detail shortly, but let's look what happens here. Remember that when the BIOS looks for a bootloader on your drives, it identifies a bootloader through a magic number, which is a word or 2 bytes, sequence of 2 bytes. And this is that magic number. It's basically a signature that identifies all this as a bootloader. So it basically just tells the BIOS, hey, I am a bootloader. I'm a valid bootloader. Please consider me. And then the BIOS says, oh, cool, I'll load you into memory. The actual magic number is here 0x55AA, but remember that we're working under a little Indian architecture. So the least significant bit is saved lower in memory, okay? So that's why if you define it as a word, you need to reverse the bytes here. So it's 0xAA55. Okay, so those are 2 bytes that are located exactly at the end of our bootloader, okay? So then that means that we need exactly 510 bytes before those 2 signature bytes. So that explains what's happening here. The times directive followed by a number tells the assembler that we need to repeat this x times, okay? So we need to define 1 byte, 1 null byte, x times. So that's pretty straightforward. Now what's happening here? I'm taking 510 and then I'm subtracting something from it. Well, all of this must be 510 bytes. So what we need to subtract from 510 is what we already have in here up to this line, okay? So let's say if all of this was 100 bytes, then we only need another 410 bytes of zeros, followed by these 2 bytes of our signature. So here, the dollar symbol, as you remember, is the memory address of the current instruction. So here, and the double dollar signal refers to the start of the code, the start of the file, basically. So if you subtract from the current memory location, if you subtract the starting memory location from that, then you get the length of all this code here. So that's what dollar symbol minus $$ means. It's the length of the code up to this instruction here. So if we take 510 and subtract that length here, we get the correct number of bytes that need to be 0 filled. So that's what this instruction does, and then, as we said, our magic number follows. Okay, so let's just minimize this for now, and I'm going to show you how to build this bootloader and how to run it and test it. Let's ls here. Now, what I do to make things easier for me is to create a Makefile. I'm not sure if and how to make this in Windows or Mac OS. I think in Mac OS it works the exact same way, but Windows I'm not sure. Regardless, you can do just fine without a Makefile. It's just an easier way to do it. On Windows, if you can't create a Makefile, you can probably create a batch file, a command line script that will do the same for you. So let's just get this cat Makefile, and this is the contents of the file. So basically, I define a label called boot. And then there's a tab here, and it's important for you to use tabs, because if you use spaces, it will fail. So boot :tab, and then you need to specify a list of files that you want to work with, and currently we just have one file, so it's boot.asm. And finally, on a new line, you tab again and you enter your command. And this command here basically compiles our assembly file and creates a flat binary file. So it's nasm-f bin for binary, space the name of the file, boot.asm, -o for output, and the name of the output file, which in my case is just boot.bin. And finally I have another label that allows me to clean up the files. So this uses the boot.bin file, and if it finds it, it just removes it using the rm boot.bin instruction. So if I ls here, you can see that I've already created the boot.bin file, and if I do make clean, then it's just removed my boot.bin file. And now if I do make boot or simply make, then it creates my flat binary file. Let's take a quick look at our flat binary file first. So let's do vim boot.bin, and as you can see, it looks very funny, but that's because we're looking at this in text mode. So let's switch to hex. And to do this in vim, you type colon and then percent bang or exclamation mark and xxd. Hit enter, and boom, now you have hex. Yeah, so this is where our hello world string is. So basically all our code and data is this up to this point. Very little code, and then as you can see, everything else is zero filled. It's zero filled until we get to this part here, which is our magic number. And as I've said, the actual magic number is this, 55AA. Remember that in the code we defined it as a word AA55 in reverse order, which is because of little endian. And if you have no idea what I'm talking about, check out our previous videos in this series. Okay, so to demonstrate that this is exactly 512 bytes, actually in this case it's 514 bytes, because for some reason my editor is adding a carriage return and new line at the end of the file. But the important thing is that byte number 511 and 512, those 2 bytes must be this. What follows after this signature is simply ignored by the BIOS. The BIOS will only load up to this point here. It will ignore whatever comes next. So yes, you can add more than 512 bytes into your bootloader, but those will be some useless bytes because the BIOS will discard them. Anyway, 200 in hex is, and let's open up our whiteboard a bit. Okay, and we have 0x200 in hex. This is index 0, this is index 1, this is index 2. And remember how we translate from a base to base 10. this basically translates into this 0 times 16, which is our base because it's hex, to the power of this 0 here plus this 0 here times 16 to the power of this 1 here plus this 2 here, 2 times 16 to the power of this 2 right here. So this obviously is 0, this is 0, and this is 2 times, and 16 to the power of 2 is 256. If you don't believe me, use a calculator. And this is exactly 512. So our flat binary file here up to this point is exactly 512 bytes. But then it has some 2 extra bytes here, which is just a carriage return and line feed, basically a new line. Okay, let's close this without modifying it. Clear. And now I'm going to show you how to run this bootloader using the QEMU emulator. So QEMU system x86 64-FDA, and this is this tells QEMU that we want to simulate a floppy disk, basically, and then we give it the name of the flat binary file. Hit enter, and voila. Booting failed, booting from hard disk, boot failed. So the BIOS was first trying to find something on the virtual hard disk, it didn't find anything, and then it looked on the floppy disk and it found our bootloader, and our bootloader just prints out hello world. Hello world. Okay, let's close that. And finally, I'll just do a very quick explanation of the code because I hate not explaining stuff, but we'll be looking into all this in much more detail next time. But anyway, what I'm doing here is I'm initializing my data segment here. So DS is the data segment register. And but you can't load it directly using an immediate. You first need to enter the value into another register or into a memory address and then load it in the data register. So into the AX register, I'm moving the segment where our bootloader is loaded by the BIOS. And remember, that's 07C0. So I'm initializing the data segment with that value so that when I do things like this, when I try to reference a variable from my data section, it uses this as a segment. So 0x07C0 colon, and then the offset of this variable here. Okay, and that just avoids me having to type this all the time. So I can use, or actually, since the data segment is not properly initialized, that will not work either. So I will have to do something like this, 0x07C0, and then the label each and every time I try to reference a variable, and that's a pain. So this is much easier. Okay, and I'm also setting the ES segment register to the same value, because I will be calling the BIOS here. The BIOS provides some functions basically that the bootloader can call. It's like an API if you must. This is called an interrupt because what happens is it actually interrupts the current flow of the program and gives access to the BIOS, and then the BIOS returns to our code here. We'll be talking about interrupts in more detail soon. So this specific interrupt looks into ESBP for a string to write on the screen. So this interrupt is used to print a string on the screen. So ES is initialized with our segment here, and BP, the base pointer, holds the memory address of our string here. So I'm loading the hello world memory address into BP. Then 13 and hex must be loaded into the AH register, 1 byte register, in order to tell the 0x10 interrupt that we want to print a string. So the 0x10 interrupt does some other things as well, and depending on what you place inside the AH register, it knows what you want it to do. In the AL we place the value 1 to tell the BIOS that we want the cursor updated after printing the string. If we place 0, it won't update the cursor, so the cursor will stay in the same location. BH holds the page number. It's basically to write on the current page, it's page 0. Then BL holds the color attributes, and let's see, I'm going to leave this link here in the video description so you can check out the BIOS color attributes. Basically, each character printed on the screen is 1 byte, but it has another byte attached. So for each character you need 2 bytes, and one of the bytes is called a color attribute, and the first 4 bits in that byte hold the background color, and the other 4 bits hold the foreground color. Okay. And I'm using 0 for the first 4 bits because I want the background color to be black, and F for the foreground attributes, which is in binary is 1111 F, because I want white text. Then into the CX register, I'm moving the contents of the data. Well, I'm moving the contents referenced by the memory address string len here. So I'm actually moving the value 15. Make sure to define this as a word here, because you're moving it into CX, which is a word register. If you define it as a byte, sometimes you'll get unexpected results because it will load 2 bytes. So it will also load 1 byte from whatever is below this. Or another option would be to define this as a byte and then load this into CL and then move 0 into CH. Okay. Let's see. And finally, we have the row number and column into DH and DL respectively. For the row, I'm using the 11th row, or B in hex, because as you previously saw, if we run our bootloader, the QEMU writes some stuff on the screen as well, and those are exactly 10 lines in my case, so I'm writing starting from line 11. Otherwise, if you don't specify that, or if you set it to 0, it will overwrite the previous text basically. And then I'm calling the BIOS interrupt 10, and I'm making the bootloader hang and loop infinitely. Okay, so I think that's plenty of info for today, possibly too much info. Sorry about that, but that's how it goes. We have a lot of things to cover. I hope you enjoyed this and found this useful, and until next time, have fun and keep studying. Also, don't forget to subscribe and hit the bell so you can keep getting notified once we add new videos. See you next time.